So, good afternoon, everyone. My name is Sujoy Ray, and I work for Wiwynn and currently responsible for the design and development of OpenRMC compliant Rack Manager solution for our OpenEdge platform. Before I start my presentation, I'd like to take this as an opportunity to thank entire OCP team for organizing such a wonderful event during this unprecedented time of human civilization. We are in the midst of a global crisis, not only for our families, friends, colleagues, and customers, but for the entire human race at large. The global COVID-19 pandemic has forced us to reinvent how we work, learn, communicate, engage, and socialize. Cloud computing has played a crucial role in addressing various needs during this challenging time, enabling businesses, providing various tools to governments for crisis management and help to maintain the continuity. The cloud computing is everywhere. So a big thank you to you all in the OCP family for working relentlessly and innovating the life-changing solutions for the entire world. Right now, our healthcare and essential workers are on the front line of battling the novel coronavirus disease, which is spreading rapidly throughout our cities, state, and nation. They are putting themselves in the path of this virus. On behalf of Wiwynn family, I'd like to take a moment and thank them for their selfless dedication, help, and support. Without further ado, let's proceed with today's topic. So today, here is the agenda. First, I'm going to talk about the system overview. In this section, I'm going to provide brief description of our EP100 platform, which is primarily being used as a development vehicle for this project. Second, I'm going to talk about the system boot up and SLED discovery. In this section, I will talk about how the system boots up and discover the various SLEDs. Third, I'm going to talk about features supported by the firmware stack. In this section, I'll provide a high-level summary of the firmware stack. Next, I will talk about the Northbound API Support, which we are currently working on. And in this slide, I will touch base about our design decision and plan. And last but not the least is call to action. This slide will describe how one can join the community-driven effort. So why don't we start with the system overview? The Wiwynn's EP100 are the optimal 3U flexible edge platform targeted for teleco, O-RAN, and edge computing. It retrofits directly to existing teleco racks and other innovative space-saving designs to address limited space requirement. This open edge platform has front accessible serviceable network and management cables, power ports, and swappable rack managed RMC. It contains two power supplies which supports both AC and DC in to fit to various remote teleco locations. In addition to this, we have like the flexible SLED design. It supports various application workloads and it can be easily reconfigured for different SKUs. Each SLED also offers Intel AEP and M.2 carrier OCP 3.0 NIC for different 5G edge computing applications. Currently, we are working on developing the Rack Manager solution to support the legacy management topologies. So with this system overview, now I'm going to talk about the system boot up and SLED discovery. So for this RMC design, we are using AST2520, which is ASPID's 6th generation server management processor. It is an ARM11 CPU running at 800 MHz. In terms of DDR support, it supports both DDR3, DDR4, We have SPI flash, which is being used as non-volatile storage, and other IP blocks to support various server management functionalities such as I2C, GPIO, PCIe, fan tachometer controllers, PECI, etc. So what happens after power on? The hardware state machine transfers the control to the U-boot running at U-boot at shift select 0. It is the design requirement that within 22 seconds the watchdog timer 2 must be disabled. If not, the RMC would be reset and system will start from the second SPI flash. Now U-boot performs the basic system initialization such as DDR memory, then copies the Linux kernel from SPI to DDR and transfer the control to the kernel entry point. Next, what would happen? The kernel will decompress itself. It then sets up system functions such as essential hardware and memory paging, and then calls start kernel, which then performs majority of system setup such as setting up the interrupt, setting the rest of the memory management, device driver initialization, etc. Finally, the init process, which is the user space process, gets executed. And next, our RMC stack starts running and it gets initialized. The SLED monitoring task is spawned at the end of RMC stack initialization, and this task is responsible for discovering and monitoring the SLEDs. The SLED presence pin, we have like a dedicated pin to indicate whether a particular SLED is connected in the slot or not, and this SLED presence pin indicates the RMC about the presence of particular SLED in the designated slot. Now, next, each SLED has a dedicated IPMB bus, and this IPMB bus is used to query various SLED parameters, including IP address. Now, if the network cable is connected, each SLED will be assigned with a particular IP address, and once that is available for subsequent communications, we will be going through the LAN interface instead of IPMB. Next, I'm going to talk about the overview of our software stack and the system. The green layer at the bottom is basically the hardware layer, and we can see AS22520, which is being used as the RMC controller chip, and this interfaces with various hardware components. The system provides two PM bus compliant PSUs, each capable of providing 2 kilowatt of output. We have 64 megabyte SPI flash, which is used as a primary storage. There are E-square prompts to store through information for RMC board, PDB board, and backplane. Each PSU also provides their respective flows and support firmware upgrade feature. There are temperature sensors in the RMC board, and you can see that already in the green box, and as well as in the backplane to monitor the temperature. Now, when it comes to measuring the key system voltages, the ADC block of AS22520 is used to measure various voltages. This is to ensure that proper functioning of the system. The network switch connects RMC to the network, and also it provides a path to control the SLEDs. Next layer, which we can see here in the diagram, is the kernel and the boot support package layer. The universal bootloader, popularly known as U-boot, is primarily being used as a bootloader for this system. Now, it is responsible for initializing the hardware and, most importantly, the DDR memory, which is used as an XIP memory for the Linux kernel. U-boot uses the flattened device tree to configure hardware blocks such as GPIO, serial ports, and other hardware devices which are being used for the bootloading process. In addition to booting the Linux kernel, U-boot also provides a monitor mode features, and currently we are expanding the capability of that monitor mode for various hardware diagnostic features such as memory testing, I2C bus stress testing, etc. The Linux kernel, we all know it provides certain services such as memory management, process management, device drivers, etc. Then the RMC stack basically widely uses various device drivers such as GPIO, timer, watchdog, LAN, I2C. They are all mentioned in this block, and those device drivers are widely being used by the application layer. All onboard peripherals such as temperature sensors, power supplies, EEPROM, etc. are connected using I2C. In this system, basically I2C is the main onboard peripheral communication interface. Next, I'm going to talk about the application layer, and this is the blue part of the it's a blue part of the diagram. First, it is the IPMI stack. It is the heart of the system. It implements the IPMI protocol layer. Then we have like IPMB, IPMI interface is used to gather various SLED information. In our current design, we are not planning to implement the southbound specification as outlined in the RMC group, but this will be implemented in future. Then SLED mount task, which is one of the tasks that is running under IPMI stack. This task is responsible for communicating with the SLED. As we discussed previously, the system supports hot insertion, removal of the SLEDs. Then SLED mount task basically is responsible for implementing necessary housekeeping jobs for each of the SLEDs. Next, we have like sensor mount task, which is another thread responsible for monitoring various onboard sensors. This also works under IPMI. Next is the Redfish layer, which provides the RESTful interface. In this design, various sensor and SLED informations are gathered by IPMI layer. Then this information is also consumed by the Redfish layer for the monitoring purpose using the REST interface. The control action generated by the Redfish interface is serviced by the IPMI layer. Another application layer we have is in the form of light HTTPD. This layer provides the web services. It is an open source web server optimized for speed critical environment while remaining standard, compliant, secure, and flexible. Next layer application we have like in the form of BusyBox. It is popularly known as the Swiss Army knife of embedded Linux. We all know about it. This software suite that it provides several Unix utilities in a single executable file such as VI, ls, fdisk. And I'm not going to discuss much details about BusyBox because it is outside of the scope. In addition to all these applications, the RMC stack provides various user space tools for easy hardware debugging such as I2C app, ADC app, and GPIO app. These applications comes very handy. For example, in case of I2C app, one can scan the bus, initiate read-write transaction to any I2C device, and they are all executed from the RMC console. And widely, I have seen like how helpful this can be during some hardware troubleshooting. Now, in addition to all these tools, we have also ported the Linux, one of the popular Linux application called PARF under our software solution. The PARF we can use for optimizing and performance analysis of the system. So with that, let's go to our next topic, which is the features supported by our format stack. For this project, we have used, for this project, we have used the AMI stack, which is basically 12.3, and what that means, it's version 12 and update 3. And this actually helped us to accelerate our development and shorten our time to market. And this release comes with Linux kernel 3 and as well as Linux kernel 5. We have chosen to use kernel 5 for better security. For the IPMI compliant functions, below at the bullet points, you can see that what we support. The current stack is basically IPMI 2.0 compliant. Threshold sensors such as voltage, temperature, etc. are supported to monitor the system health. The system event log is also supported. Currently, we have allocated approximately 256K for this purpose. In addition to this, we support flu, SDR, etc. The IPMB is mostly used for in-band communication between SLED BMC and the RMC. The RMC uses dedicated NIC-based network to provide an interface of IPMI messaging over LAN with IPMI 2.0 messaging protocol. RMC LAN supports RMCP Plus protocol as well. And we also support standard IPMI command sets. Now, the next important item that we are working at this moment is basically integrating the Redfish solution. So for Redfish, we are using the Redfish Scalable Platform Management API specification, which is version 1.8, and the schema that we are supporting is 2019.2. In addition to this, we also support DHCP. Then we have RMC heartbeat indicator, RMC firmware update. RMC firmware can be updated using AMI Yahoo Flash and Web UI, and hot insert and hot removal of the SLEDs are supported, and we do support the firmware upgrade of the power supplies. So now I'm going to talk about the Northbound API support, which also we are currently being worked on. So the strategy that we have adopted for this whole Northbound API support, we wanted to first get everything working using IPMI. Next, we are going to develop a shim layer for easy data and command exchange between IPMI and Redfish layer. Then we are going to integrate Redfish and implement the Northbound 1.0 specification. So currently we have, as we have discussed, that we already support like hardware inventory, power and thermal telemetry, rack level power capping, etc. through IPMI. Now as a next step, like we need to make all this information available through Redfish, and also we'll be modifying the Redfish to be compliant with the Northbound specification. That is being worked on at this moment. So with that, I will be going to my last slide, which is the call to action. So here I would like to share one personal story. Like I started joining this hardware management project and OpenRMC project from March, and I found that like the amount of work and that information that this whole group provides to the community is amazing. So I'll strongly encourage those who are listening to this presentation, please join the mailing list. Then you can subscribe the project. You can go to the also the sub-project page. The link has been provided. And if you want to join the regular call, you can click on the third link, and there is a calendar available at the bottom of the page. You can see when the team meets. So with this, I would like to end my presentation Thank you very much, and I'm open for questions.
Hey, thanks, Sujoy. Very good presentation.
Yeah, thank you.
And yes, as Sujoy said, please join Hardware Management Project. We are looking for more and more people to contribute. John, Kelly, do we have any questions on the public conversation? John, you're on mute. Okay, here is a question from John.
Yeah, please. Yeah.
He's asking, will you be contributing this product design to OCP? That's the question.
That's a good question, actually. We need to, definitely, I think for the software stack, maybe we'll be contributing as a binary. I'm not sure whether we can release entire source code, that we need to look. But that's a very good question. And we need to look into this.
Okay. Thank you.
You're very welcome.
I have a question also on, so I do see right now your implementation is basically you have support for Redfish, but also for a number of internal facing communication, still reliant on IPMI.
Yep.
So my question is, IPMI has known security concerns, legacy issues. What is your thought on to move on to more modern standards like PMCI that DMTF has developed and others have adopted?
Yeah, as I said, it will be the next phase. You're right that we need to move into that direction, So first we need to get something working, because we didn't have the RMC solution in the first place, So get everything working with the proven technology and then move into the next step. That's the approach we are taking at this moment. But yes, we will be there.
Okay. And do you see any gaps that you see today in moving that legacy implementation or your current implementation to?
No, actually the SLED has to support each SLED should be conforming to the southbound specification, and that is being worked on at this moment. So yeah, as soon as we have that, we should be able to make that switch.
Okay. Thanks, Sujoy.
You're very welcome.
Okay, let me ask audience, anybody has any other questions? Okay, in that case, let's thank our speakers. Sujoy, thanks again for the presentation.
Yeah, thank you, Hemal. Thank you, John, and thank you, OCP team. You have done a fantastic job during this time.
Oh, you're welcome. Thanks.
Yeah, okay.